Okay. Good day, everyone. You are welcome to Module 2 of this lecture, Design and Simulation of Electronic System using implementation of 5-volt DC power supply for microcontroller applications as a case study. In Module 1, we have already introduced ourselves. This lecture is brought to you by Embedded System Team, Mechatronics Department, Federal University of Technology, Owerri. So, just for benefit of doubt, in case you didn't listen to the first lecture, we just have to introduce ourselves quickly again. My name is Engineer Dr. Ekene Samuel Mbono. So, I will hand over to Gospel to introduce the rest members of the team. Gospel, when I point the mouse to each individual, you mention the name of the person. Is that okay?
Okay, sir.
So here we go.
Good everyone. This is Mr. Chibike Peter.
Okay.
This is Mr. Lucky Fine Chidera.
Okay. Can
We
you see me?
have Miss Yes, sir. We have Miss Ayaun Faithful Chinaza.
Okay.
Okay. We have Mr. Obi Prince Chukwuemeka.
Okay.
Then beside him, we have Mr. Bariel Daniel.
Okay. So who is this person?
This is me, Mr. Okechukwu Gospel Chibike. Thank you, everyone.
Okay, let's give him a thumb up, a round of applause. Okay. So we move down to Module 2. We've all discussed this. We've discussed what electronic engineering is all about. The basic difference between electronic and electrical engineering has been discussed. We've differentiated between active and passive components in electronic system. If you have not subscribed to our channel, please, you can do so now. Now, this is Module 2. When we talk about design, we have to start from, when we want to design anything, you get to start from load analysis. Load analysis. What do I mean by that? You want to build a house. You don't just start foundation without knowing the weight the foundation is going to carry. No, you don't do stuff like that. So when we say we want to design power supply for any system, it is basic, it is fundamental it is normal. It is engineering practice that you start by your load analysis. You want to know what load is your power supply going to power. Did you hear what I just said?
Yes, sir.
Yes, sir.
So you don't start designing power supply. After designing power supply, you now bring in the load. It's not engineering practice. No. Now, in as much as this lecture is just for 5-volt power supply, we want to use this lecture to demonstrate, to showcase how engineering design is done. So in this case, we assume we are powering an Arduino board, and we want to assume the worst case scenario where all the pins of the Arduino board are engaged. So we begin to do our load analysis. You see, we have A0 to A what?
A5.
A5. And from data sheet, the maximum current consumption of each analog channel is 40 milliamp. Now, Arduino Uno has 13 digital input-output pins, and each of them equally takes maximum of 40 milliamp. There is if you look at my mouse, there is 3.3 volts terminal there. If you are going to use it, the maximum it takes is how many milliamp?
50 milliamps.
Okay. So putting them all together, we have 20 by 40. I mean, from serial number 1 to serial number 20, we have 20 by 40. We want to get the maximum current, then plus 50. And that gives us what?
That gives us
Go ahead and talk.
it's not really, is that multiplication of, okay, that gives us 650 milliamps.
650
850 milliamps.
milliamp. Okay. So if we are going to design a power supply, that power supply should be able to supply at least 850 milliamp. And then the operating voltage of Arduino Uno, as you all know, is 5 volts DC. Having done that, we are designing a power supply of 5 volts that is able to supply 850 milliamp. Are we on the same page at this level?
Yes, sir.
Okay. So let's go to materials now. Based on the load analysis, 7805 can give us 5 volts and the maximum of 1 amp. So it's 150 milliamp above 850 milliamp. So it can give us what we want. And then we have a electrolytic capacitor. I am aware that there are off-the-shelf power DC power supply you can use for Arduino. You can buy them from markets, AC to DC power supply, those things are there. But as an engineering student, you get to know how to design these things because the off-the-shelf power supply you are buying from the market is somebody that designed them. They didn't come from the moon. So we're going to learn this thing. Imagine that we have our AC supply in the lab. How do we bring that 240, 220 AC voltage to 5 volts? We want to look at the principles. So we have electrolytic capacitor that will help us do filtration. Then we have rectifier diodes that will help us in rectification. And then the step-down transformer, LED that will indicate when power comes, and the resistor that will help us protect our LED, and of course, Arduino Uno as our load. Let's proceed. We're actually talking about the materials. This is the transformer, this is jumper wire, this is the regulator, this is capacitor, this is the resistor, this is the LED, this is another jumper wire, this is Arduino Uno. We're still on materials. Eventually, when we finish the design, we will mount it on variable board. So we will need soldering lead, soldering iron, jumper wire, flexible wire to connect our AC, and adaptable box to package our power supply, and then the glue gun to be able to get some things, components in place inside this box. We proceed. Now, let's get to the design now. If you are going to use any electronic component as an engineer, you must make reference to the data sheet. Please, can any of you tell us what a data sheet is? What do you understand? What do you think data sheet is all about?
Okay, good day everyone. My name is Obasi Kelechi Justice. A data sheet is the manufacturer's manual for that particular component. That is the specification of the component, the working principle, and the high amount of voltage that can come into the component and the rest. Thank you.
Excellent, excellent. Data sheet gives us information, electrical characteristics, voltage characteristics, dimensions of the component. Excellent, excellent. Let's give him a thumb up. Let's clap for him. So, with respect to 7805 or the greater series, we have LM78 series. We have 7805, 7806, 7808, 7809, 7810, 7812, 7815, 7818, 7824. All these are in one data sheet. Once you get the data sheet, you see the spec. And part of the spec is what is being shown. From the data sheet, you get to see that if the black end of the regulator is facing you, the left side, the left pin is the input. The middle is the ground, while the right-hand side, the pin on the right-hand side is your output. If you supply voltage 3 volts above the expected output voltage to any of these series, you are going to get a regulated output, meaning if you are going to work with 7805, the minimum voltage you should supply as the input is what? Did you get the question?
No, sir.
I mean, the input voltage should, for safe operation of this IC, the input voltage should be at least 3 volts above the expected output voltage. Now, for 7805, what is the least input voltage you are supposed to supply to it for you to get a regulated 5 volts?
Okay,
8
eight
volts.
8 volts, sir.
8 volts, that's correct.
8
What
volts.
of 7815?
18 volts.
18 volts. Good, perfect. And that should also inform the transformer you are going to use. Because if you are working with 7815, for example, you can use 220 12-volt step-down transformer. It doesn't fall in. But if we are interested, just like in our project now, 7805, we can work with 220 12 volts because it will definitely give us what we want. These are the absolute maximum ratings. These are the absolute maximum ratings. Input voltage, Vr 5 to 18 volts. You don't supply more than 35 volts so that your system will work as expected. I don't even expect you to supply just 3 volts above the expected, above the output, so that you don't end up hitting your regulator unnecessarily. Then these are the working temperatures. I think we are blessed. We are on temperature here is friendly, so we don't need to worry about the temperature. The room temperature here is between 25 33. So that's just that. We proceed. These electrical characteristics. The typical output is 5.0 volts. So anytime minimum is 4.8 and the maximum is 5.20, meaning that when you have finished designing your power supply with regulator and you are getting anything outside these two ranges, it means that something definitely is wrong with your circuit. Is that okay? Is that taken?
Yes, sir.
Okay. So we proceed. That's it on regulator. We go back to step-down transformer. The voltage ratio of secondary voltage transformer is actually a device that helps us to transform energy from one form to another. It's an electromagnetic device. When you supply voltage to the input winding, it will, through electromagnetism, by electromagnetic induction, it converts it transfers the energy to the secondary winding. From primary winding to secondary winding, there is no contact. It is done by electromagnetic induction. So we have that the ratio of secondary voltage Vs to primary voltage Vp is proportional to the ratio of turns in the secondary and the primary coils. What somebody should read the equation there. I want to be sure that you are still connected. Read this equation. We can call it equation what? 1. Let's call it equation 1. But let's continue. Read the voltage equation, please.
Okay, the voltage equation,
Yeah.
the ratio of the secondary voltage Vs to the primary voltage Vp is proportional to the ratio of the turns of the secondary Ns and the primary Np coils. That is Vs over Vp equals to Ns over Np.
Okay. So it's equal to that. Now, another person read the current equation there. This one.
Okay, so by Rob Daniel, the second equation states that current ratio for an ideal transformer, the current ratio is the inverse of the voltage ratio. That is IS over IP is equal to NP over NS. That's primary current over secondary current over primary current is equal to number of primary turns over number of secondary turns. Thank you.
Okay, excellent. So we proceed. Now, when you combine the two formula, you get that Vs upon Vp is equal to Ns upon Np is equal to Ip upon Is. Power conservation, efficiency of transformer in this situation is 1. That is, efficiency is 100% because power, which is defined as IV, is Vp Ip equals Vs Is. But we know that in reality, it cannot be 100% because there is always losses. In fact, when you power your transformer, when you energize your transformer, over time begin to notice that the transformer is heating up. So there is energy loss. It can't be 100%, but ideally, a perfect transformer gives us efficiency of 100%, but we can't get this in reality. Now, electromagnetic equation, that's EMF equation, electromotive force equation of a transformer is given by E is equal to 4.4 times F times the number of turns times the electromagnetic flux. You need to take note of the formula. Induced root mean square voltage. We get to know what root mean square voltage is all about later in this lecture. F is the frequency of the source, N is the number of turns in the coil, while phi is magnetic flux in the core measured in Weber. Turn ratio. The turn ratio is defined as the ratio of primary turns to secondary turns. For a step-up transformer, you notice that the number of turns of secondary winding is greater than the number of primary winding. That is for a step up. For a step down, the reverse is the case. Transformer efficiency. In practical applications, efficiency is never 100% due to losses like copper loss and iron loss. So transformer is output power now over input power multiplied by 100. Now, let's discuss root mean square voltage. We understand that sinusoidal signal is not steady. It changes from positive to negative. Are we on the same page with respect to that?
Yes, sir.
So when you
Yes,
consider
sir.
this figure where my mouse is, you notice V2 is greater than V1, V3 is greater than V2. Now, I don't know if you have you done any course on integration?
Yes, you have.
Yes, sir.
Okay, so integration is actually addition. When you say you are integrating, you're actually finding the area. You are integrating something somehow. You are adding that thing up. So if we integrate the whole of this will be the starting point to the ending point. We are going to get the average of this area. Another way to do it is to take V1 square, V2 square, V3 square, V1 square plus V2 square plus V3 square plus V4 square. That is the value of the voltage here, plus V5 square up to V12 square. We add them up and find the average. That is, divide them by 12. When we do that, that is what is called mean average, mean square average. Means, just a minute. Okay, so when this is square, produce square up to this point, when we calculate the average is mean square average. Are we on the same page? Do you understand that?
Yes, sir. Yes, sir.
So by the time we take the square root of the whole thing, it becomes root mean square average. And that will give us a rough idea what the average DC voltage is. That is what actually it is. It is you are going to get a value, the average value of this area. And that value is what is called root mean square average. Essentially, when we measure the voltage, AC voltage, like what we did in the lab, that was on Thursday. What we did in the lab, those AC voltage we're actually measuring with multimeter is not the peak value. It is the root mean square voltage we're measuring. Also, we saw from the oscilloscope that oscilloscope will give you root mean square average and also will give you peak. What is the mathematical relationship? Mathematical relationship is this. V root mean square average is equal to what? Somebody read this.
Okay, V root mean square average square is equals to V peak divided by root 2.
So that's that. That's that. And then for full wave rectifier, which is our concern in this course, V peak, V root mean square is equal to V peak over root 2. Now, somebody compute, if you are with your calculator there, what is root 2? What is root 2? What is value of root 2? I'm waiting for your answer.
A value of root 2 is 1.4142.
You say?
The value of root 2 is 1.4142.
Okay. So if we have root mean square of 170 volts, what's actually the peak voltage? Let's assume that we measured an AC signal with a multimeter. It gives us 170. What actually is the peak voltage of that source?
240. 240.
240. 240. Good. Why are we interested in measuring the root mean square? AC voltage constantly changes, making the average voltage zero. Root mean square provides a meaningful measure of the voltage heating power capability, often called the effective value. The effective what? Value. So, that's that. And it helps us. Another thing is that it helps us to calculate power. You want to calculate power, you just, if you have your root mean square, you don't need to do any other conversion. If power is IV, you can just use it to calculate your power directly. You will just treat it as, once you get your root mean square value, it's the same thing, it's equivalent of DC voltage. So you can use it to compute the power consumption of the system. You can see that here. Power is V square root mean V square over R, where V there is root mean square. You know that power is IV. Is that correct?
Yes, sir.
Yes, sir.
Yes, sir.
Power is IV, but then I, based on Ohm's law, is equal to what?
Current.
Yeah, current is equal to, based on Ohm's law, Ohm's law tells us that V is equal to IR. So I is equal to
Yes, sir.
what?
R is equals to V over R.
V over R. So if power is IV and the I is equal to V over R, it means that power is V times V over R. And that gives us V square over R. So are you convinced how this equation, are you convinced now how this equation came about?
Yes, sir.
Yes, sir.
So we continue. Why RMS is used power calculation, it allows engineers to use familiar DC power formula. I've already explained that. Instrument measurement, most AC voltmeters and multimeters are calibrated to display the root mean square value. Components rating. Electronic components are rated based on RMS voltage, not peak, to ensure they can handle the power dissipation. Okay, so that's that. I think this is part of what we did in the practical section. You can see that. You see, remember this when we were checking our transformer. You remember when we took VRMS, when we took this reading with oscilloscope. Do you remember?
Yes, sir.
Yes, sir.
This
Yes,
is
sir.
the output of the step down transformer, 220. 240 to 12 volts transformer. This is the output. Is that correct?
Yes, sir, it is.
So our meter was reading 11.7 and the oscilloscope was reading 12.2. Of course, we don't expect two of them to be the same, but it shows us that the meter was actually measuring the VRMS and not the peak voltage. That's that about transformer. What are we doing? Let's remember we are trying to look at the theoretical aspect of the power supply. All this while, that's what makes you the difference. Anybody can bring a transformer, bring a capacitor, bring diodes, and connect them together, and declare for himself or herself and say it's working. But as an engineer, you need to know the engineering principles and theories behind what you are doing. That what makes you a designer. So a diode is a semiconductor that allows current to flow in how many directions?
In one direction.
In one direction, from anode to cathode. And there are key things you need to take note of, or one needs to take note of when you are working with a diode. One is the forward current. You must not exceed the forward current. Number two is the reverse voltage, peak inverse voltage or reverse voltage. You must not exceed that. If you exceed that, you are going to break down the voltage. And what else? Yeah, basically, these are the two things. You take note of the forward current. If a diode is rated 1 amp, don't pass more than one, don't even pass up to 1 amp to that diode. If you know you are going to pass more than 1 amp or close to 1 amp at that point, use a diode that has higher rating, maybe a diode that has 2 amp rating, so that you don't take the risk of spoiling your system. So that's that. And then another thing you need to take note of is the diode, the voltage across the diode while in working condition. For silicon diode, what is the voltage drop across the diode? Who remembers?
0.7.
0.7,
The
correct.
diode
0.7. And for germanium diode, what is the voltage drop? That is 0.6. Is only when the voltage across the diode is above that threshold that you will see the current, the voltage, the diode begins to conduct in the positive direction. Now, this is the data sheet of IN400 series diode. For IN4001G, the PIR, that's the repetitive peak reverse voltage or peak inverse voltage, is what?
is 50.
50. And for 4007 is 1000. Please let's take note of
1000.
this. And this is it. We proceed now. Application of diode. Having known that diode conducts in one direction, if this is a typical bridge rectifier circuit, now when this is an AC source, just assume that here is plus and here is negative. If here is plus and here is negative, that is, I mean, the positive cycle. Just imagine that we are here. Then here is plus, here is negative. Then D1 will conduct because here is positive. D3 will be reverse bias. Then here is negative. D4 will be reverse bias. D2 will be forward bias. So the current will flow from here through the load, through D2, and go back to the source. When here becomes positive and here becomes negative, it means that D1 will be reverse bias, D2 will be reverse bias, here will be forward bias. So current flows from D4 through RL and then through D3 back to the source. And in that way, since the current direction in the load or through the load is always in one direction, we say that we have rectified the AC source. We have rectified the source to now have a unified AC current. This is still AC. This is still AC. Later, you will see that this is the frequency of this is actually twice. The frequency of this is twice of this frequency. Let me see. This is what we mean. Let me see if we can run a simulation. Can we? Look at what we mean here. If we run this simulation, this is a typical rectifier circuit. If we run this simulation, we are going to get this. So apart from many other things this circuit is showing, I want you to observe this. I want you to observe something. Can you see that within a cycle, this is the source, the one in orange, that is channel A, is the source. Look at it, is the source. It's coming from the source, that's channel A. Then channel B is the output of the rectifier. When you watch this, let me pause it. Let me just pause it at appropriate time. When take this reference from here to here is a cycle. Is that correct?
Yes, sir. Yes, sir.
From
Yes,
here
sir.
to here is a cycle. Can you notice? Do you notice that within this cycle, this rectified voltage has gone 2 cycles? That is 1, 2.
Okay. Yes, sir. Yes, sir.
So please note that after rectification, the frequency of the signal here is always twice the source frequency. If the source frequency is 50 Hz, the frequency here should be how many Hz? I want to be sure you understand what I just said. If the frequency
Sir,
of
please
this,
repeat what you said.
if the frequency of the source is 50, what should be the frequency at the output of the rectifier?
The frequency should be 0.
It's going to be what? Then it means you didn't understand the explanation here. Look at within one cycle, this one makes double cycles. So
It's
if the
100 heads. 100.
it's going to be 100 Hz. Exactly. It's going to be 100 Hz. It's going to be 100 Hz because just if we double this to 4, just watch the output now. Watch the output. What the output will look like. Can you see what is happening?
Okay. Okay. Yes, sir.
It begins to increase, but at any instant in time, from here to here, this is a cycle for the source. This is always double. The output is always double. Is it clear to you now?
Yes, sir.
Okay, we proceed. Let's go back to our slide. We go over to capacitor. An electrolytic capacitor is a polarized electronic component designed for high capacitance in a small volume, typically using an aluminum, tantalum, and niobium oxide layer as dielectric. These capacitors are crucial for smoothing power supply, voltage fluctuation, filtering, and energy storage. They must be connected correctly based on polarity, or they may fail. If you pick a capacitor, the longer leg is always the what?
Longer leg is the positive.
Is always the positive terminal. Correct. It's always the positive terminal. For an electrolytic capacitor, the positive terminal is always the longer leg. You can even see it on the body. The shorter leg is always labeled negative. You can see it. Look at it. You can see it there. It follows the same pattern with LED. So this is the internal structure of capacitor. You see the negative terminal, the positive terminal. In between them, you have your dielectric. Okay. The same thing happens. What we intend to show here is to make you have a visual understanding of the internal construction of a capacitor. This is positive, this is negative, and then you have your dielectric. Once you do that, you will create a what do you call it? You will create a charge. Actually, the way to form a capacitor, just get two plates together, two materials together, connect one to positive, connect one to negative. if you bring them together, but don't cause them to touch, you have already formed a capacitance. You have already formed a capacitance or a capacitor, because if the distance between them is actually A, then A becomes your dielectric. But then the capacitance will be very small. What makes your capacitance big or small depends on the dielectric material. You can see this one: electrode, electrode, insulator is the dielectric material. So if you connect here to positive and connect here to negative, you've already formed a capacitor. And then this is the capacitor the inside of the capacitor we normally see in our local market. Okay? Mathematical model of an electrolytic capacitor. If you are going to charge a capacitor, when you close this circuit, the capacitor will charge through the resistor. If you want to discharge the capacitor, once you remove your power, the capacitor will discharge through the resistor. At least you saw in the lab, we were able to see in the lab that when we remove power from our power supply, it takes time for the LED to go off. It takes a little time. Is that correct?
Yes, sir.
So
Yes, sir.
Yes, I think
what
I
actually happened is
think
that
I
we
remember.
open the switch here. Capacitor has to discharge through the load. In that case, that arrangement of resistor and LED. That's exactly what happened. This is the equation for the discharge. Please take note of this. One good thing about engineering is that equations don't change like that. They are there. Even if you want to do your PhD, you still come across the same equation. This is for the charge. Time T, RC is always a time constant, is the product of R and C. As we progress, you will understand what time constant is all about. Charging voltage equation, I've already explained. When a capacitor is charged through a resistor, the voltage increases exponentially, asymptotically approaching the supply voltage. That's that. When this T goes to infinity, you notice that Vc tends to Vs. As time progresses, as time increases, this component, exponential component, will go off, will tend to zero. And once it tends to zero, Vc becomes equal to Vs. Vct is voltage across the capacitor at time t0. Vs is the source voltage. The resistance is the resistance you connected in series with the capacitor in ohms. And capacitance is measured in farad, not in microfarad. If you have microfarad, if you are given microfarad value, if you want to compute the RT, you must convert that microfarad to farad. Time is the time constant. When T is equal to 1, that is, at time constant of 1, the voltage will have reached 63% of V source. Okay. This charge equation follows the same pattern, only that time constant will now be about 37% of V0. That is initial voltage of the capacitor before you start discharging. I expect you to take time and go through this, understand this, form a very good background and basis for your engineering practice. We've discussed this. So this is the pictorial representation of what I've been saying about capacitor. So this is the charging curve. This is the discharging curve. This is the time constant. This point is the time constant for charging curve. This point is the time constant for discharging curve. And then the formula for charge on a capacitor is always equal to CV. That is the capacitance multiplied by the voltage on the capacitor. And energy is always determined by E is equal to half CV squared. I think this is your basic physics. So we progress. We progress. Application of electrolytic capacitor, we've already said this. I think this is one of the things I demonstrated already. So we progress. I've demonstrated this already. The only thing I need to mention there is that you can see that the value of C affects your output. Let's run this simulation again. We'll return it to 1. Now, this is the filtered voltage. Can you see my cursor?
Yes, sir.
This is the source voltage. This is the voltage without capacitor. That's point B. That is B. This is the filtered voltage. So the capacitor has filtered the voltage. It's almost DC now. Let's increase that capacitor to, say, 1,000. 1,000. You will see the effect. You see the filtration capacity has increased. You reduce it. If we reduce the capacitance to, say, just 100, the ripples will be much. The ripples will be much. You can see the screen?
Yes, sir. Yes, sir.
So you get to understand this thing practically. Let it not just be a theoretical knowledge in your head. I expect you to understand this thing. That's why the visualization is coming. We progress. So where are we? I think we are here. We move. So this is source voltage, output with capacitor, output without capacitor. This is already explained. Now, here comes the equation for ripple voltage, and ripple voltage is always VDC over 2F multiplied by C times your RL. VDC, you can substitute here VRMS. They are the same thing. We move. Peak-to-peak ripple voltage, this has been said. We continue. If you are watching the video, you can pause the video and look at it in details. Finally, let's talk about light emitting diode. This one won't take much of our time. It conducts light emitting diode. Is a highly efficient semiconductor device that converts electrical energy directly into light via electroluminescence. When forward biased, electrons recombine with holes at p-n junction, releasing photons. Less offer long lifespan, low power consumption, and no warm-up time. Once you power them, they come up, and they come in various colors. Okay, the working in principle is simple. Forward bias the diode by connecting positive source to positive terminal and the negative of your circuit to the negative terminal, the diode begins to conduct and lights up. The caution there is that you need to, depending on the voltage, you need to use a series resistor so that you don't burn off your LED. That's it. If you observe your LED inside the leg with small plate inside is always the anode and is always a longer leg. You can visit electrical for you for further instruction on this. That's the reference. We proceed. The symbol of diode, light emitting diode is there. The outgoing 2 arrows shows that it's emitting light. That's what differentiates it from ordinary diode. And then this is the caution. I've already mentioned it. LEDs generally need a series resistor to prevent excessive current from damaging the component. And that's that. When you bias, please pay attention to this point. LED requires forward biasing to emit light, typically operating between 1.2 volts to 3.6 volts, depending on the color. So if you are going to bias a diode, LED, you need to use this formula to find your R. See, we are gradually building up your capacity to design. You need to know the value of the resistor you are using. It's not because they say 220 volts resistor, 150, 1 kilo ohm. You get to know what you are doing. You use this formula to calculate the value of your resistor, so that even if you are supplying 15 volt DC, you should know what to do. Is that taken?
Yes, sir.
Yes, sir.
I hope my students have not slept off.
No, sir.
No, sir.
Okay, so we take an example. To drive a 2 volt LED from a 5 volt source at 2 milliamp, that is, you want 2 milliamp to pass through the LED, you simply do 5 volts minus 2 volts over 0.02. So you get your 150 ohms. That will be your series resistor. If you want to increase the current, then you can substitute the value of the current you want to use here so that your resistor value will decrease further. That's just that. And then this is the table for different colors of LED. They don't have the same forward voltage. Red has the least, followed by yellow, followed by green, followed by blue, followed by white. Okay. So this is the end of Module 2. Thank you for listening. We expect you to subscribe to our channel today, like and share the video, and answer the tutorial questions on the comment section. These are the tutorial questions to let us know that you really followed the lecture. Let me just read number 3. The longer leg of an electrolytic capacitor is always the negative terminal. Students, is that correct?
No.
No, sir.
So the answer is
It's
false.
false.
Please tell us the location from where you watch the lecture. We want to know your location. Okay, we are going to pause here. When we come back, we now do the simulation. We've already concluded our design procedure. So when we come back within a few minutes, we do the simulation. Thank you for listening.